We are currently on LinkedIn, as well as we're currently on YouTube. So if you have any questions, you can just go ahead and ping us there, in addition to the Zoom that we're currently on. So I'm going to do a really quick short introduction. Today's awesome Seattle Spark+AI meetup session that's also being broadcast on Databricks LinkedIn and Databricks YouTube is with Mario DIRAC and Colin Slater on why data is eating the universe, the coming age of massive sky surveys. And it's really cool because we get to talk about not just Apache Spark and Delta Lake, but we actually get to talk about killer asteroids and dark energy. So without further ado, I'm going to go ahead and stop talking because, in fact, I'm pretty sure you really want to hear from Mario and Colin. So, Mario, why don't you start by also providing a quick introduction to yourself to let everybody know who you are.
Yeah, thanks, Danny. Thanks for the invitation to come in and talk about this. Yeah, this talk is going to be a bit about a mix of astronomy and big data issues and analytics. So my name is Mario Juric. I'm an astronomy professor at University of Washington and the director of an institute called DIRAC that we have on campus, which stands for Data Intensive Research in Astronomy and Cosmology. And I'll be co-presenting with Colin Slater, who's also here in DIRAC, and he is part of the Rubin Observatory Data Management Leadership Team. And we'll tell you in a second what Rubin is. It's probably, at least to me, the most exciting project in worldwide astronomy at this point. To give you a brief intro of kind of where we come from and what do we do, as I mentioned, we're at UW. We work in DIRAC, and what DIRAC is, it's a center on campus to advance and support research with complex or large astronomical data sets. So we're talking about tens to hundreds of terabytes up to petabytes and tens of petabytes. And we do this by supporting people and communities, researching and building next generation of solid technologies in astronomy. So kind of we like to start things and experiment with things that a couple of years down the road become widely used and standard elsewhere. We're sort of love to pilot technology. And that's how we got into Spark actually many years ago at this point. So let me start talking about the topic here. And I'll begin, not really at the beginning of time, but I'll begin kind of in the 80s, and we'll get to where we are today. So first of all, we're astronomers, right? We're not software engineers or computer scientists by training. And when you go to Google, the way I learn everything is I go and type in the query in Google, and images can tell you more than words. So you type what's an astronomer in Google, and this is what you get back. You type what's a professional astronomer, you essentially get the same list of images, more or less. It's basically a person and a telescope. And a person is usually standing next to a telescope or looking through the telescope, observing the sky. And a lot of astronomy really did work like this for a while, for at least 300 or 400 years. So your typical workflow, this is kind of more what a professional astronomer looked like, is you would decide on an object of interest. You would try to get telescope time. It's a time where you actually lent a big telescope to go and observe it. You take the images of that object in spectra, which used to be done on photographic plates. You bring them back home. You'd analyze them using kind of analog mechanical instruments. You can go in and look for either the shape of the object or the brightness. You try to understand what happens. You'd publish the results and conclusion. So this kind of process would give you something like maybe you could do this once or twice a year. You can get one to a couple hundred, a couple of thousand objects. This was it. It was really hard. It was a lot of hard work. The 90s of the last century were an exciting time for astronomy because they changed almost all of that, right? CCDs really started being used on a regular basis and became larger and larger. We started having, coupled with that, we started having computing clusters that enabled us to actually analyze many more images that we could do manually, like you saw in the slide before. And of course, there was the internet that allowed us to share all of that, not just beyond just the one person who took the data. So suddenly, astronomy was in this regime where observing, rather than being extremely difficult, became easier and easier. So data could be collected, telescopes got more automated, analysis could be done more easily because you get everything directly on your computer, on your screen. And we could scale up by about a factor of 10 or 100 just in that decade from the introductions of computers and automation and CCDs. So then people started thinking, right? Like our classical way of working was, let's take one person, one telescope, and let's go observe one to a few objects. But now the number of objects that we can go and observe has actually grown dramatically. So instead of observing one object, the question was like, why not now? Why not just go and image everything? Instead of picking which object you're interested in, let's go image everything, and then we'll pick the interesting one later on, and not just us, anyone, if you make that such a data set public. And this is really where surveys, astronomical sky surveys started kicking in. So what do you need to do to image everything? To image everything that's in the sky? You need to build a telescope with a very large, what's called a field of view. And that's basically how much of the sky telescope can observe at the same time. To give you an illustration, like one of the things people don't quite realize is in these telescopes that you hear about, like the Hubble Space Telescope, how small is the field of view in the sky that they can observe? So what I'm showing here are the footprints of the 4 different cameras or instruments on the Hubble. And whenever you see those images, they look beautiful, they look detailed, they seem like they're huge, they're massive. But if I scale this to the size of the moon, of the footprint of the moon in the sky, which is something that you have a feel for how big it is, that's how big the field of view of Hubble is. It's tiny relative to the moon. So if you wanted to image the entire sky with something like the Hubble, right, that would take a lot of time. What you really want is something that can take big images, where like this frame, this blue frame that are drawn here is sort of, can take a couple of moon sizes at the time, and then you can go and tile the entire sky with this. So people went ahead and started building these kinds of telescopes. What you need to have coupled with this, you need to also have a large camera, because you remember how small that Hubble field of view was? It had a camera of many megapixels that cover it. So now you have a much larger field of view. If you want to retain similar resolutions, you have to have really massive, much larger cameras. So that was the other thing that happened. Here's an example of a telescope and the camera that really revolutionized this astronomy, that really kickstarted this whole survey business. It's a 2.4 meter telescope on the right at Apache Point Observatory. And what you see on the left is the CCD camera, the mosaic camera that sat on the bottom of this telescope. Now it's at the Smithsonian. It's probably one of the most important kind of astronomical artifacts over the past quarter century or so. 126 megapixels, and remember, this was 1998 when this was built, and it's just huge. But the combination of these allowed us to go and start really mapping out almost the entire sky. And the third thing you need is, now you're mapping the entire sky. Now you have the images over everything, and you just don't have enough astronomers, don't have enough humans to go and look at each one of those. So the third kind of prong in this approach was to automate observing and data processing, and then make all those data available online. So the images, back in the day, you would go to the top of the mountain, you'd look at your one object, and you would actually look at that image and do something with it. These days, that kind of analysis is automated. So the telescope observes, the camera records the photons. We get digital images out of what's in the sky, and then that's fed to data analysis pipelines that basically detect which objects are present in the image. They detect their sizes and shapes. They measure how bright they are. And what we get in the end are not images. What we get in the end are databases. It's a database of object positions. At this point in the sky, I've seen the following object with its properties. And such databases are then made available online for astronomers to query. So we went in a short time span of a couple of decades from going to the mountain, sitting at the telescope, and then looking at photographic plates, to sitting at home in front of a laptop typing SQL queries. So I'm leaving it up to you to decide where you want it to be, when you want to be an astronomer or not after this change. But that's kind of why astronomers today have much more in common, probably, the folks on this seminar than than maybe your classical astronomer 20, 30 years ago. So these databases with large sky surveys are now getting into interesting territory in terms of the amount of data that's in there. So the SDSS that I showed had about 500 million objects observed with about a billion observations, 1.2 billion observations. But now we're getting into a regime where there are going to be billions of objects and trillions of rows in the databases that are to come. And what we do with those is we typically plot things in sky coordinates. So we look at maps of objects in the sky. Like in this representation, each dot here is a representation of just a small subset of objects from the SDSS database. And the other thing we do is we keep re-observing the sky. So we can look at how these objects change in time, whether they change brightness, whether some of them move, like the asteroids. So we'll look at time series as well. So we have a problem of storing a trillion row database that can either be thought of as something that's spatially partitioned or spatially interesting, and which also has a time component to it. So like each of those data points is actually a time series of how the object behaves. So you're starting to see where this goes and why we're starting to like Spark. Before I go on and talk more about that, just to answer one question, like, did it work? This idea that we can go ahead and image the entire sky and that will produce great results for astronomy. And the short answer is yes, it worked wonderfully. SDSS, this really first large digital sky survey, imaged about 40% of the sky. Here's just a selection of the kinds of things it's discovered. So most distant quasars ever know. It discovered that the Milky Way galaxy is actually gobbling up smaller galaxies that are around it. Detected something called the baryon acoustic peak, which allowed us to understand, which gave us a different line of evidence for dark energy. Produced the largest catalog of multicolor asteroid observations, et cetera, et cetera, et cetera. And to quantitatively kind of put that in perspective, I ran this query yesterday. I actually never done this before yesterday, but SDSS, this one telescope and one data set resulted in 3,000 publications with almost 240,000 citations. And that probably means nothing to you unless if you're not in the field. But let's compare it to something that everybody knows about. Let's look at what the Hubble Space Telescope did using the same metrics. And you can see that this, our little dingy telescope in New Mexico, like 2.5 meter thing underground, when you compare it to the Hubble in these metrics, they're extremely comparable, right? Hubble had about 3,200 publications with 170,000 citations. So this shows that this idea of let's image the entire sky and then unleash that data set to the world and let people use it to produce science really is valid. And it's a wonderful example of what you can do with new technology and new data management tools. So this really opened the floodgates. And we went from SDSS being this one survey to now there being many of them. So this is now the footprint of a number of different telescopes that are taking big data sets in the sky. And here's our moon, and here's our Hubble Space Telescope field of view down here. So you can see that the new ones are just even larger, even bigger. One that we worked on here at UW, this is Wiki Transit Facility. It's ran out of Caltech. It imaged something like 2 billion objects, and each object was imaged about 100 times. So we have 200 billion row data sets. And the really big one, the one that Colin and I spend almost all of our time on just building it at this point, is going to be the legacy survey of space and time. So this will be the largest survey ever undertaken. It's currently being built in Chile on a mountaintop called Cerro Pachón. It'll repeatedly, it's almost done, as you can see. That this is not a rendering. This is a real building. It'll have its first light in 2023 and start operations in a bit over 2 years. So it'll repeatedly image the sky. It'll generate about 60 petabytes of raw data of images. It'll image about 40 billion galaxies, asteroids, and stars, and result in a data set of about 30 trillion observations. And this telescope is really why we started thinking about data issues in astronomy where Spark is becoming necessary, because now we're at a point where we have too much data. It was easy when you were one astronomer with one telescope and one object to look at. Now you've got 40 billion of them. And now everything turns into a big data problem of sifting through that data set, either statistically summarizing it or finding the most interesting object. So how do you do that? How do you take these large data sets and turn them into knowledge? These days, the way data management in astronomy works is that most of these large data sets are in what we call astronomical archives. And this is not a zip file. This is like an institution, a building with many computers that house these data sets, typically in RDBMSs with images and file systems. There's some kind of web front end. It's usually a fairly simple interface where you type in SQL queries and you get subsets of that data out, you as a user. Through the web browser, you run a query, you download a subset, and you would run analysis locally on the supercomputer that you have at your institution. And that worked wonderfully for the past decade or so. But that paradigm is about to break down. Like ZTF already has 1 trillion detections, or is working its way towards 1 trillion detections. This new machine that we mentioned, legacy series space and time, that will go up to tens of trillions. Even if your query is very selective, so even if you get 0.1% of all the data, when we look at the sizes we expect to be data set, that's still going to be a terabyte. So terabyte is a huge subset to download. And typically this download is the first thing you do. You do some analysis, you tweak your query, you download again. So you don't have to do many of these. So what are we going to do now when we have to download a terabyte every time? Well, there's one observation, which is that the analysis code one uses for any particular project actually is much smaller than anything we have in the dataset. So I looked at all the codes I've written in for my previous papers, and typically like the logic, the new logic that I write is an order of 50 to 100 kilobytes. So rather than bringing data to the code to analyze it locally, let's bring the code to the data. Let's just run the code where the data is. So we're going to have our archive architecture that kind of looks like this, where data is in some building somewhere in the US or in the world, and I download it for analysis locally. I'm just going to move the analysis resource into the same building. So I'm just going to upload the code. I'm going to make the web front end much richer. So typically we use things like Jupyter notebooks, and there's some interesting kind of portal SkyMap type views for visualizations. But I will do all the analysis in the archive, therefore alleviating this problem of how do I get large subsets of the data out. Now, this is what we're currently doing. Like this is what the astronomy is building towards for the next, I'd say, couple of years. But there's still issues that remain. Like for one, now our archives need on-premise and user compute resources, and they need a lot of them. There are a few of these data sets, like the LSST data set, that serve the entire community. So now you just have to serve thousands of power-hungry astronomers, power in the sense of computing power, with the computing that you have locally. And that requires large upfront capital investments. The elasticity becomes limited and ends up with small per user allocations. So in order of 10 cores or a couple of terabytes per user. And yet the data set is petabytes in size, and the users really would love to go through that entire data set rather than just all subsets, because they want to find the most interesting objects in there. This still uses traditional RDBMSs, and the analyses are very difficult to scale because there are bottlenecks there. You cannot do something like you typically do with Spark. The whole workload let Spark parallelize it. And another big issue is that I've talked about LSST as kind of the next big project. LSST is the largest, but there are a few more that are on the same scale. And time again, we've discovered that we've discovered new things in Astro when we brought data sets from different instruments together and analyzed them together. So for example, you have something that you image in the optical, something that you image in the infrared. You really want to cross-match those two and see, like, this object that I see in the optical, or this object that I see in the infrared, it doesn't exist in the optical. Why? Because there's a shroud of dust around it. Why? Because this might be a star that's just forming planets, and therefore it's very interesting. So those kinds of things are super powerful. But if all these data sets are now petabytes in size, and they live quite literally on opposite parts of the country, doing that kind of joint analysis becomes difficult because you basically have to figure out a way to collocate a lot of that data before you can even run queries. So what do we do there? Ideally, what you'd like is for these data sets somehow to come together so that they're in the same place with a lot of compute capacity, so I can run queries and joins like this fairly straightforward way. So what do? We build a national facility for large astronomical data sets. Do we do something else? And Colin and I are going to talk to you about, are going to argue for the something else part here, which is that we already have a natural place where we can do this kind of co-location, and it's called the cloud. So instead of building yet another building somewhere to put all these Astro data sets, why don't we start shifting that entire industry onto the cloud? And basically, in putting them into ideally the same data lake somewhere on the cloud, in the same region, well, a couple of copies in different regions. But the point is that you want them virtually co-located. That way, you leverage existing storage infrastructure. You don't have to build anything up. Build big building plus a lot of computer. You have nearly infinite computer sources because we have big data issues in astronomy, but the industry has even bigger data issues. So those resources from our perspective are infinite, as long as we can pay for them. And then the industry is really thinking about this, like Spark, Delta Lake, next generation of whatever Denny and his colleagues in Databricks come up with of those technologies, and then we get to use them for almost with no effort for doing science. And that's the second part of this, right? You put things on the cloud, you need to have a way to analyze it. And our argument here is let's adopt standard big data analysis tools. And so you leverage massive investments, leverage all the work that people have put in, but also there are some things that we uniquely care about that can be broadly useful and that we in academia can implement and then push upstream. So like some of the changes that we've done to some of the optimizations that we've done to Spark SQL Optimizer to Catalyst, right, are an example of that, and we hope to push them upstream as well. So everybody benefits. And this is really where Spark kicks in, because it's the tool that can handle this scale of data and the scalability that we need. So to be able for an average astronomer to go through a couple of petabytes of data and joining these data sets, that's the goal that we want. And so far we found Spark to be by far the most stable and advanced solution there. So that's kind of our vision here, that any astronomer can scalably jointly analyze any data set of any size. And when we say any size, think petabytes, think petabytes worth of catalogs. And so what will that take? Think that solution based on prototypes so far is cloud plus Spark plus some interesting changes to data formats and some astronomy-specific extensions. So I'll hand it over now to Colin, who's going to tell you about those extensions. We call this the Astronomy Extension for Spark. And we adopted that name because we used to call this project the Large Survey Database, and then YouTube's algorithm really hated that acronym and wouldn't let anyone under 18 watch our videos, so we switched it to Spark. Okay, so I'll stop sharing and hand it over to Colin.
Okay.
I have to admit, I still love the idea of a large survey database acronym. I do have to admit, I like that.
It's certainly, whenever I would give that talk at Berkeley, they nodded approvingly.
Well, it makes sense. We're talking about a bunch of folks up here in Seattle, and then a bunch of folks in Berkeley. It's sort of on brand. All right, Colin, you ready to go?
Oh yeah, if it looks good to you.
Definitely, rock on. Let's go for it.
Okay, so Mario just gave a great overview to sort of the landscape of astronomy and why we're so focused on these big data problems in astronomy. And I'm going to kind of give you the deep dive into how we've tried to solve some of these problems over the past few years and how we've used Spark for that. And so we've built a system that we call the Astronomy Extensions for Spark, or AXIS, that are really designed to make it easy for astronomers to tackle all the problems that Mario described. And this is sort of a multi-layered solution because it includes some aspects which are sort of strong conventions about how we want to lay out data on disk in order to make it accessible and easy for astronomers. We've added Python convenience functions that sort of make Spark speak the same language that astronomers expect when they're trying to do their analysis. And we've also implemented optimizations that make the typical astronomy use cases really fast for astronomers. And so we've been building for several years. And we've also been doing real science with this for the past several years, using data from some of the most recent observatories. Because we're academics, there's a paper that goes along with this. So all of the details describing how we implemented this, and also things like performance benchmarking and comparisons to other solutions are all in this paper that's available in archive. And because we're also in the software world, there's a GitHub link that you can get the actual source code and all the details at. So I'm going to kind of give you three different dives into how we work with this, talking about maps, talking about light curves, and talking about cross-matching. So when we first thought about AXIS, when we first thought about Spark, our goal was really to study the structure of the Milky Way. And that's kind of a different problem because the Milky Way is all around us. Like, you have to see all the stars in the sky, or a large fraction of the sky, in order to understand how we fit into this large galaxy that we live in. And so we need to use these surveys that image such a large portion of the sky. And we also need to be able to do analysis that involved the entirety of these catalogs. We need to look at all the stars to find how does their position on the sky, what does that tell us about how the Milky Way works, how the Milky Way formed, how the Milky Way evolves. And this was really our first foray into Spark, because this really gave us the ability to look at the entire database at once. And so just to start bringing up some pretty pictures, a simple way to think of this is I can just make a map of the Milky Way just by plotting how many stars are there in any particular patch of sky. And that's what this is here. It's not an image. It's actually just a counting of how many stars there are per square degree. And you see the sort of big band structure here. That's the disk of the Milky Way. When you're out at a very dark place and looking up at a clear sky, and you see that kind of diffuse band of light, that's what we think of as the Milky Way. But the Milky Way is more than just that. It's all around us. And so we were able to make these maps with Spark a matter of minutes, and that really blew us away. Like, we just could type a SQL query and do histograms to make these sorts of analyses. And really, it's not just that we want to make that one map. A great thing about being able to use Spark is that we can sort of follow up and make other selections, like say, well, what if I only want to look at this particular point in the galaxy? What if I want to look at this part of the sky? What if I only want to look at young stars or old stars? They tell us different things about the structure of the Milky Way. And so we typically use AXIS and Spark in a Jupyter notebook in a Python environment, where it's really easy for us to follow up and kind of dive in an exploratory fashion to learn more about what we're seeing in the database. So here I've just zoomed in on one of those big features in the big map, which is the Large Magellanic Cloud, a galaxy that lives nearby us. And again, we're looking at numbers of stars, not an image. You can see all the detailed structure of that galaxy. So that was great. We were super happy with that. But as Mario described, there's a lot of the latest observatories are really starting to focus on how the sky is changing. They're trying to understand what's the time domain telling us about astronomy. And so we call when we have one of these observatories that looks at the sky repeatedly, we get that history of a given object, and we call that a light curve. And so we've also extended access to handle these light curves. And we thought about, well, what's the use case that astronomers want to handle? How do astronomers want to start doing their science? And their first question is that, well, somebody who works on supernovae, exploding stars that get brighter really fast and then sort of gradually dim, they want to look at the entire database and they want to find all of the light curves that might be a supernova and then do some science based on that sample. Or there's also stars that just sort of, they kind of vary in brightness. They get brighter and they get fainter, and they get brighter and fainter because they're literally oscillating. They're getting bigger and smaller over time. They do basically for millions of years. And so the people who work on that want to go find all of the objects that are varying in that way so they can study why are they varying, what are the properties of that star. This picture here is a light curve of a supernova where you see the object getting really bright and then gradually getting fainter. And so our users wanted to be able to access these really quickly and say, okay, give me all the supernovae in the database. So we needed to understand how do we store the data to enable that type of access. And we wanted the measurements to live kind of adjacent to all the rest of our knowledge about a given source on the sky. And so we found that Parquet's array columns actually are just the right amount of structure for this. I've kind of copied a little bit of one of our databases here just so you can see that, like, for any given position, RA and DEC are kind of like latitude and longitude on the sky. So at that point, we can measure how that object is varying in magnitude or brightness, and when we've measured that object. And so to put all that with array columns, we can essentially put all that data in one place. And then a user can write their analysis code to look at that without having to do any data preparation. They don't have to do a big join to find all the measurements for an object and then a group by. It's all there, ready to go, ready for their analysis code. And this works for our users because they're almost all coming from a Python environment. So if I'm somebody who studies supernovae, I have a piece of code I used in order to fit the light curves of supernovae and tell me what are the properties of that. And so it's worked really naturally for their users to take that piece of analysis code, put it into a Python user-defined function, and then call that as part of a Spark query that just runs on every single row and says, well, what's the likelihood that this object is a supernova or a variable star or some other type of exotic transient object? And then the problem is, from the user's perspective, is simple. Spark does the rest. Spark distributes this load out to all the compute nodes, and it runs it on all 2 billion objects and returns to the user a list of what the most likely candidates are. So that's been like sort of just the right amount of data structure for that use case. And I'll give one more kind of dive here into how we do cross-matching. This was also something that Mario mentioned about how we want to take the information that we're learning from different telescopes and combine that all together. The telescope on the ground looking at the optical emission, the light you can see with your eye, is telling you something that's very different than, for example, like an X-ray telescope is in space. And so to get that full picture, we want to know, well, what is it doing in all of these different wavelengths? To do that is a little bit tricky because there's no stars don't have labels on them that you can just read off of on the eye. If I want to see the same object in both telescopes. I just have to know that, well, it's at this position on the sky in this as seen by this telescope, and the same position as seen by the other telescope. But that's always a little bit inexact because there's a little bit of uncertainty in these measurements. And so we're always looking for sort of the nearest neighbor in a sense. And so when I want to look at all of the objects observed by the observatory and find their matches to a different telescope, I need to do that nearest neighbor computation for basically all handful of billion objects in my catalog. And this is something that our goal really was to make this fast enough that it could be on like an interactive time scale. We didn't want this to be something where you did it once and then you were kind of stuck with the results and hopefully it was good enough. Otherwise you have to run another cross match overnight or for a few days. We wanted to take sort of minutes time scale so I could adjust the parameters. I could bring new data sets and try it again and see what am I learning by adding this new data set, that new data set on the fly. And so we've solved this with basically a spatial partitioning system that matches a query optimization that we've added to the Catalyst engine. So we do, this is a sort of esoteric partitioning system, but we take the sphere, so this, the sky around us, we think of as a sphere, and we split it into very long, thin partitions that wrap all the way around us. And so we split into a couple hundred, maybe 1,000 partitions, not just the few on the image. And then inside of those partitions, we sort the data from one end to the other. So the Spark+AI file literally has like all the objects at the top of the partition over here, and then goes down the line until it wraps all the way around the sphere. And the reason we do that is because if we do that same partitioning system for all the data sets that we want to cross-match, then the process of joining these two data sets and the process of finding these nearest neighbor matches is just a matter of working down that table A and the same partition table B kind of sequentially one by one with this moving window. So for every record in table A, there's only a small range of potential matches in table B, and we know how big that window needs to be because we've specified some sort of range of allowable values that might be good cross matches. And so we can essentially take step by step through this table and move the moving window in the right way in order to find all of these nearest neighbors for an object. And so the end result of this is that queries for the cross-match for an entire database of 2 billion objects do finish in matter of minutes, 10 minutes or so, depending on how many computers you have running on the same task. And so this really does make it a part of the user's exploratory analysis and not a thing that they think of as really onerous and they want to run overnight. And that because we've done this purely in SQL, the optimization is just a SQL optimization. It's actually available for other uses that might benefit from this type of query structure. Essentially, anytime I want sort of not just matching values, but matching plus or minus some sort of range, our code will identify that in the query plan and then say, okay, we can solve that with this moving window solution instead of the typical join process. So those are my sort of 3 dives into light curves, into map making, and into cross-matching in Axis. And so with this, I will hand it back to Mario to say a little bit more and wrap up.
All right, thanks, Colin.
Excellent stuff, Colin. Thanks very much. All right, back to you, Mario. You're doing good?
Yep, here we go. So Colin gave you kind of a deeper dive into how we actually use Spark. There's an even deeper level of that dive that we invite you into questions if you want to know how we actually implemented some of those optimizations. They are on an issue. We're trying to get them upstream into Spark. That need a little bit of work and cleanup before that can happen. But like the big thing for us here is avoiding shuffles. Like that's our entire life. Because you have a petabyte worth of data set here, petabyte worth of data set there. You don't want to shuffle that whenever a user runs a query. So most of our optimizations are, as I'm sure many people on the call, like how to avoid shuffles, how to tell Spark that the data set is already cleverly pre-partitioned and things like that. So anywhere where you have those kinds of applications, I think we might have a lot of things to talk about. What's next for us in this work? One of the things that we're starting to look at is how Delta Lake can help. One of the reasons why I love the large survey acronym was then I could say that we have ACID on LSD or the other way around. But things like Delta Lake could bring transactions, could bring make it easier to update data sets. And actually setting up this set of data lakes with large data sets, that's something that we're moving towards so that we're ready for LSST in about 2 years. So I'll close with this slide by basically point out that we're now at a point where the work in astronomy with Spark is going from exploratory to more of let's get ready to do some really serious science. And we're building up a team of about a dozen software engineers and data scientists to help develop software systems for key LSST science cases, including data infrastructure like what Colin just talked about and what I introduced. So if you're interested in this sort of thing, we are this project, this group is split in Seattle and Pittsburgh. So us at UW and our colleagues at CMU, we'll be looking to hire about a dozen people. We'll be looking for Spark developers, data scientists, cloud engineers, front-end devs, DevOps folks, and then just simply Python, Scala, and JavaScript generalists to build up the data infrastructure and then the codes to do things like solar system exploration. So we want to utilize these data to find where all asteroids and where all potentially killer asteroids are in the solar system. We're writing algorithms for that. For time domain science, like the light curves that Colin was showing, for extragalactic astronomy. So understanding what dark energy is, what dark matter is, those are all things that now depend on us extracting knowledge from those petabytes of data that we're about to be collecting. And that's where Spark comes in. That's where software comes in and algorithms go in. So we really are looking forward to this and are looking for people to join the project and help this halo of a couple hundred astronomers who know the physics of it, but don't necessarily know the data science aspects or the software engineering aspects of the problem to really help build the tools and then enable basically the next 10 years of discovery in astrophysics. So if you're interested, follow us on LinkedIn. We'll start posting job openings soon. I think we still have to go through some paperwork, so it'll take another like 2 or 3 weeks. But then we're looking to hire up quickly and get this built up so that in 2024, when this telescope goes online, we're ready and we can start discovering things. So I'll stop here and thank you, Denny, and thanks to everyone who came to hear what we have to say, and let's open it up for questions.
Perfect. Mario, Colin, thank you very much. If you have any questions, please prop them into the Zoom or to LinkedIn or to YouTube. We've got an old friend of ours, Daryl, who, this is to you, Mario and Colin. And it's probably, I already answered in LinkedIn, this is most likely off topic, but I figured I'd just ask the question anyway, which is there a plan to expand to monitor objects that might be on collision course for Earth, right? So it like, and then also like maybe this is where I think we're going a little off topic. The collision course for Earth, yes, but then where it's also being used for planetary defense, and that's what I was saying. Like that's more like a DoD type question, or or whatever else. But please, why don't you answer that, Mario?
Yeah, it's not as off topic as you think. Yes, like one of the big things that this telescope. Let me show the telescope. Where's my telescope? Here's my telescope. One of the big things that why this is being built is to discover about 80%, 70 to 80% of all large asteroids that can potentially, in fact, collide with Earth. And like we have, like one of my graduate students right now is developing algorithms to find them in these data sets. So if we find something, this is like one of the places where an astronomer hopes that they will never find what they're looking for. Like you don't usually get that, but here, like this is one of the things where we hope we never find it. But if we do find it, like at that point, DoD and others get involved. But finding it is an extremely computationally intensive and complex thing. It's not as easy as writing a SQL query in the database. It's basically a combinatorial problem where you want to try out like every point in a database with every other point to see if it's consistent with something that's moving on an orbit in the solar system, and then you want to determine if that orbit is crisscrossing or crossing the Earth's orbit. So it's a really cool problem to work on. And like this solar system exploration data point here is about that. So if you want to come save the Earth, come to UW.
Excellent. That is a great segue to say, I just posted the DIRAC.us/LinkedIn for the openings. So if you're interested in learning more about the positions, by all means, go ahead and follow the DIRAC here, and then you'll get to learn more about helping to, save the planet, basically. So I think that's it for today's session. I really, really appreciate your time. Again, follow these folks on DIRAC.us/LinkedIn, and thanks very much for this fun session for the Seattle Spark+AI Meetup and recast on Databricks LinkedIn and Databricks YouTube. Thanks very much, everybody.